Okay, my name is Sweekar, and today I'll be presenting my work on hydrogen use cases in Kotzebue. Uh, we have been like talking about Kotzebue as like one of the remote community, which is like 30 miles like above Arctic Circle. Uh, Similar to like the Northwest Peru, because it's a remote community, it presents its own challenges. So the diesel shipments happens like twice a year, and they're pretty much stuck with the diesel shipment. But then, so with whatever price they would have bought the diesel, they would have to like go off and continue using the same. Um, but then Kotzebue is also blessed with enormous amount of renewable power, especially in form of wind. So the goal of the project is, what if we can go off and utilize this excess wind energy or the solar energy that is available on site, and can we like store it in some form, maybe in form of like a molten salt, rechargeable battery, or also in form of hydrogen, and then like, we can use it at later point of time, and thus reducing like the use of fossil fuel. So this is like the Kotzebue energy landscape. So right now, Kotzebue has about four diesel gensets, operational gensets, six, four predominantly operating. There are about like 1700 kilowatts wind turbine to 900 kilowatts wind turbine, 500 kilowatts solar PV, and a 1 megawatt battery. With all of this, it produces like excess load that is used for both like electric purpose and for heating the hospital. Um, and whatever excess load that we have, the goal is to go off and utilize to split water, generate hydrogen, store hydrogen, and then use hydrogen to generate power again when the renewable energy comes down, so that we can go off and use reduce the use of diesel fuel and utilize like the stored renewable energy in form of hydrogen. So that's like the existing. I mean, that's like the planned energy landscape for Kotzebue. So the goals of the project is that I mean, like this energy landscape seems like pretty straightforward, very clear. I mean, there's excess renewable energy available. We can just go off and store and like use it later. But the catch is, one to store like 1 kg of hydrogen, like in a tank, it costs about 1,500 kg. I mean, $1,500 just to store 1 kg in a hydrogen tank. Um, and to generate the hydrogen requires about 55 kilowatt hour of electricity, whereas the capacity of the hydrogen is about 33 kilowatt. So the circular efficiency of like the putting in the energy and like getting the energy out of it, like the round trip efficiency for storing hydrogen is like a bit lower. So it puts a limit on like the so it puts challenges from the economic perspective. And then so the goal is to go off and figure out, does it really make sense to implement this technology? Will it make an economic feasibility? Feasible? Would it be like economically feasible? And then like, is like hydrogen like the only option? Can we go off and utilize like a bigger battery storage? Would it be like much more feasible? And finally, like evaluate various other hydrogen carriers. Again, the reason why the hydrogen carriers is also important is because hydrogen has like the highest energy density per mass. It has like 120 megajoules per kg, but it has a very poor volumetric energy density. It has about like 9 megajoules per meter cube. Just to put it in perspective, if the diesel has about 35,000 megajoules per meter cube, so it would require about 1,000 times more volume if you are if you have like a diesel tank, and if you were to store the same energy in form of hydrogen, it would require about 1,000 times bigger volume than like what the diesel tank would require. So that because of this constraint, it prompts us to go off and utilize or like store hydrogen in like various forms. It could be any of these chemical forms, and so that it improves like its volumetric energy density, and it could be utilized later. So the goal was to like go off and like assess like all of the forms in which it could be stored. Um, and so that was like one of the goals that we had. But then like where does like all of this fit in? Like why do we have to go off and do this? So as we were like pointing out earlier, so Kotzebue is like one of the remote communities. So all the tech that we go off and implement at Kotzebue would have like a bearing on implementing the similar tech elsewhere, and it helps in decarbonizing the space, not just in Kotzebue but in all the other remote communities as well. And then it also reduces its reliance on fossil fuel. um, because of all these things, it also presents a chance to go off and have like 50% plus renewable energy penetration in like the entire energy portfolio. And because of because it can go off and like reduce like the the net cost of energy to the consumer, like the end user as well. So it is like a win-win situation for everyone involved, to all the stakeholders involved, and that's the big picture of our project. Um, so like what is the research methods that was like utilized? First step is to go off and figure out like what is the sort of like hydrogen carriers that is like required, like what makes more sense, like should we use ammonia, should we use methanol, or should we just use like hydrogen in its raw form? So to go off and evaluate this, like it was predominantly like a paper study, like to calculate by hand and figure out like applying like the basic combustion chemistry and figuring out like what makes sense. Then to do an HOMA modeling, where we kind of go off and like do a baseline calibration. And once we have a baseline calibration, go off and use it to predict, to check various other scenarios, whether it would make like an techno-economic sense to go off and implement a system. And finally, we did see some limitations in like HOMA modeling, and which required the use of MATLAB scripting, which I'll get to it in a moment. In the first part, just to give an example, um, so most of the energy, whatever that we have, the renewable electricity, that would go off and be utilized in like electrolysis process, and then like from whatever hydrogen is generated, that could be stored as like a raw hydrogen, or capture carbon dioxide, and then store it in form of methanol, synthesize methanol, store it in form of methanol, and run methanol in an engine and generate power. That could be one possible pathway. So similarly, we went off and did a similar study for all the other hydrogen carriers. Diesel is at the very first, just to give like a baseline comparison. Um, as you could see, like for the same amount of energy generated, some could consume like enormously huge amounts, like formic acid, which consumes like 92 kilowatt hour. And the far right corner shows like what is the level of technology. I mean, the technology readiness level. Like some of the fuel can seem like amazing, but they are not really technologically ready to be implemented on a commercial scale. So this gives that nice overview of like what is like the carriers, like to make a decision on like the carriers that we could go off and use. Uh, and from the techno-economic model perspective, we just went off and uh, uh, did the HOMA modeling. Um, so in an HOMA, so the goal was to utilize all of the energy from the diesel genset as well as from the renewables to meet the electric load, and whatever excess energy is available, that would go off and be utilized in like the hydrogen, to generate hydrogen, store it, and run a fuel cell. And on top of it, if there is any excess electricity, even if it's available after meeting all this demand, that goes off and runs the heat load, which is predominantly used to heat the hospital. So that was how the HOMO model was set up. Kind of ran through the calibration studies, previous studies that was done by like Launch Alaska, and like the model was like calibrated. Uh, and ran a base case validations, and then we kind of like went on running the model prediction. One thing which we noted as a limitation in like HOMO modeling was that the hydrogen charging and discharge cycles is something that isn't available either in like Homer, neither in Homer nor in Zendi. So we had to go off and do an MATLAB scripting to kind of to model the charging discharge cycles. To give an analogous study, it's similar to charging a battery. We wouldn't want the battery to like charge like 20% and like discharge it and then charge again. It increases the charging discharge cycle of a battery. So the same case goes true for hydrogen. If you don't charge hydrogen tank completely and if you just like keep using randomly, it just increases the charging discharge cycle for a hydrogen tank. So the goal was, so this was what the Homer was predicting, where about 60% of the time the tank could be like empty, which shouldn't like make sense for the investment. With like the MATLAB scripting, we could see like if you were going off to implement like an 400 k or a 500 kg tank, we would have about 48% of the time when it would be like half full. So we were able to come up with like an algorithm to go off and figure out this. Um, so um, so that was like an overview of like what was like the work going on from like the hydrogen perspective. But then what is really the key challenges that we had in like tying this all together? One predominant thing was like the power curves for the EMD. I mean, EMD being a legacy engine, the data wasn't really available. We also had to encounter a couple of limitations from the software perspective. The ones that we taught like were very mature softwares had a certain limitations. So those were like some of the key challenges that we had. And what I would have done differently, I would have tried to talk to like the vendor. I mean, I would have taken the same path, but I would have also tried talking to the vendors about especially with all the buzz that is around the platinum-less electrodes, which could potentially reduce the cost of fuel cell and electrolyzer. We would have rather tried talking to figure out like the future cost. That is something I might have done differently. But then what is the key thing that we should understand is that like some of the things that we think like ammonia for a very long time was thought to be like much more inert than it actually is. But it's a ammonia is like a great fuel, to be honest. Ammonia when combined with hydrogen makes like a great fuel source. Uh, and uh, and with all the properties, so it is really very important to have like a very open mind to all the to any of the technologies before rolling it out. Um, Hydrogen storage seems like very expensive, but then there are like caveats with which we should always like work around. Softwares can be like very limiting, but then it's really our intuition which really comes to play. Our intuition and our paper cal. We might like software can tell something, but then you would have like we would have like an engineering intuition as to something might work this way, might not. So we might have to like look through it and run through some like basic hand cal, which would help build confidence in the models that we have created and the results that we are really looking at. So that I think is like my key suggestions. Um, so like what is like running through all of these systems, we kind of like came up with like a system which we like kind of proposed. But I guess like we had like a call yesterday with one of the project engineer where they are like interested in going off to install like 6 megawatt wind turbines. That kind of changes the equation, I guess now, where I mean now with all these results, like the electric utility is interested in having like 4,500 kgs of like hydrogen storage, which really drastically changes like all of our assumptions that we have been doing up till now. Um, uh, so so this is uh, the storage that was intended with the proposed system. Um, but this is like this would be changed in couple of weeks, I guess. Um, so tying it all together, battery energy storage system in like present day, if we were to like normalize it, it would cost like $700 per kilowatt hour. But then if you were to use like an hydrogen tank, it would cost 9,000 odd dollars per kilowatt hour, which is almost like 10 times the cost. But then one key advantage which hydrogen brings is that like you can store hydrogen for a very long duration, and you can store massive amount of massive amount of energy for a very long duration of time. So that's the key advantage which the hydrogen brings in. And in Kotzebue case, one of the key result that we have is that the hydrogen system is infeasible with the existing wind turbine setup. They would have to go off and install like additional wind turbine before which the hydrogen becomes feasible. Um, so this is like a chart to like show if you were to implement both hydrogen and battery together with the present cost and with the present setup, uh, the green is where like the hydrogen is economically feasible. The orange is where the 8 megawatt hour battery is economically feasible, and yellow is where both hydrogen and battery work together and make the system like very feasible. So that's how like the results look like at this point. So what are the moments I really enjoyed? It's really when like the postulates are like goes wrong. We come up with some hypothesis. We know like this will work for sure, and we just like put it on the software, try and run through it, run through the calculation. It just turns out wrong, and then I don't think that should be wrong. I mean, everything like intuition says it has to be right. It's trying to figure out like why it did not work, like what is something that like I missed out. Trying to learn the gap and like correcting something. It could be on software end, or it could be on like the person, I mean, or the knowledge that we have on the concept. I think those are the moments I really enjoyed. And yeah, the technical success, economic skills, I think is like what I really I think like gained out of this fellowship, I guess. So yeah, that's pretty much, I guess. So I'm happy to answer any questions.
So could you go back to the various different fuels that you looked at? I'm really curious about your thoughts about like the easiest to produce like liquid fuel.
So methanol is a very good candidate compared to the others.
Yeah, I'm rusty on like chemistry. Which one's methanol?
Oh, I'm sorry. The second row stands for methanol. Um, so in these cases, there's two things that we should like look at. Actually, there's actually three things that we should be looking at. One is like the electricity that it would go off and consume. But then whenever we are storing a fuel, the flashpoint column that we are saying, the temperature, that is also like really important. It would go off and define like if the fuel is if it is a combustion hazard or if it's not, is what the flashpoint would go off and define. So that is something that is pretty important as well. On the volume that it would go off and consume to go off and store it. So as you could notice, like methanol compared to like liquid methane is like pretty safer, I would say. Um, and the liquid hydrogen would need like a cryo storage. So in all those aspects, like methanol from like liquid is like a better one.
Sorry, I just thought of another question. So how is methanol produced when you're using it as a fuel storage source?
Yeah, so methanol could be produced through this process. This is the path for the methanol. You would synthesize carbon dioxide with hydrogen to go off and produce methanol with some agent.
Is that some is that I might get the terminology wrong, but is that the Tony Fisher process? It's similar to how fertilizers are produced.
It's similar to the process, yeah.
What is on your conclusion slide, what is a surge tank?
Oh, yeah. So let's say you have a scenario like this, where you have like where you have like the hydrogen which is stored in a tank. Let's say you have picked like 500 kg tank. There might be a scenario where where you might be prompted to where there might be like additional renewable energy that is still available, you might be prompted to go off and store some more before like you go off and utilize it. So it's that to cater to that additional need when your tank is like full as well, like when your primary tank is full. So that's and to balance out like any instabilities in the system. Too. So.
So I was wondering with the, you're talking about that it's relatively takes a lot of power to convert the electricity to hydrogen. Do you know how would that compare to just storing battery or energy in a battery? And then like if that's something that can be like improved on in the future, or if that's just kind of a limitation of
Yeah,
the
definitely.
technology.
Definitely, the efficiency of the system could be like improved. When I meant like it takes like a lot of energy. Just to put some numbers in perspective. Like in an idealistic scenario, to produce like hydrogen from water, it would require 39 kilowatt hour of energy. Um, to produce like 1 kg. Uh, the current system that we have, be it alkaline electrolyzers or like PAM electrolyzers, they consume like 53 to 55 kilowatt hour, which roughly comes to like 70% efficiency. Uh, as we like continue to improve upon the electrolyzer research, as we continue to have like a better electrolyte membranes and stuff, the efficiency is like going up, and we should expect some of these numbers to like start coming down in like a very near future. On the second part, when comparing with like the batteries round trip efficiencies are like higher compared to like the hydrogen. The part of it comes through like the fuel cell has like a 50% efficiency. We could like assume 50% efficiency. The hydrogen tank has its own losses. The electrolyzer has about 65% efficiency. So hence the net efficiency of the system comes down compared to batteries, which as a storage system requires very as a lesser inefficiencies compared to the hydrogen as a storage system. But the advantage the hydrogen storage system delivers, which the batteries won't, is that let's say you want to store like 72,000 kilowatt hour of a storage. Hydrogen energy system can deliver that, but the batteries aren't designed to deliver a huge energy storage. That's one thing. The second thing is, if you want to store any of these hydrogen for a long duration, you can store it for like months without having issues. Unlike the batteries, where you might like run into issues. So. Thanks a lot.